Hello again. Today in this lecture I would like to talk about the binary codes. If you remember in the uh, previous lectures when I talk about the digital systems, I said that when we want to represent the information in the digital systems or discrete elements of the information, we make a group of the bits and we call this group of the bits as a binary code. Today I would like to talk about the different types of the binary codes and show you that how we can use these binary codes in digital systems. So we know that if we have 2 bits, we can have 4 different possible combination like 00, 01, 10, 11. And if we have 3 bits, using these 3 bits, we can have the 8 elements or we can have the 8 possible combination. On the other hand, with the 4-bit, we can have the 16 elements. Now, one of the most important and significant binary codes in the digital systems is called as the BCD code, binary coded decimal code. What is this BCD code? We say that we can represent the numbers from the 0 up to 9 using 4-bit binary. So we called this 4-bit binary as BCD code. How we can do it? Using this uh, table that you can see, we say that we represent the 0 up to 9 using 4-bit. For example, if we want to represent 0 using 4-bit, we will have something like that. If we want to represent 1 using 4 bits, we will have 0001. And if we have the 2, for example, 0010 is the 2. Up to the end, all of the numbers from 0 up to 9 can be represented in this form that you can see here. Now the question is that if we have a number, for example, 3 digits number, 2 digits number, how we can represent these numbers actually in the BCD code. Look at here, in this example that I want to show you, here we have 185. So how we could represent this 185 in the BCD? We say that, let's write it here, 185 in the base of 10. Now I want to find the corresponding BCD of this number. We say that we find and write the corresponding BCD of 1, which is equal to 0, 0, 0, 1. The corresponding BCD of 8, which is 1, 0, 0, 0. And also the corresponding BCD of 5, which is equal to 0, 1, 0, 1. Now, if I write all of them beside each other, like this one, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 1 in the BCD form. This code, binary code, is the BCD of this number. So the important thing is that you have to notice to this matter, this is BCD, not binary. The binary of this number 185 is this. How we could find this binary? We talked about that. We said that if I divide the 185 by 2, I can find this number. But this BCD code comes from the concept of this binary table that you can see here. Now, I want to talk about the BCD addition, how we can add the two number which is written in the BCD code. We say that if we add two numbers which are written in the BCD code and the summation of these two numbers, if the summation of these two numbers is less than 9 and less than 9, directly we write this code, something like that. Suppose that here we have 4 and want to add it with 5. So the corresponding BCD of 4 is 0, 1, 0, 0. And corresponding BCD of 5 is 0, 1, 0, 1. Now, if I add these two numbers together, 0 plus 1, 1, 0 plus 0, 0, 1 plus 1 is 0, 1, 1, 0, 0 is 1. Now, if you look at to the 1, 0, 0, 1, means that this is equal to 9, which is less than and equal to 9. It's okay. We don't have any problem. This is the BCD summation. Now, question is that what's happening when the summation of two numbers is greater than 9, something like that. If we have 4 and 8, want to add these two numbers together in the BCD form, you can see that this 4-bit code is greater than 9. In this case, we say that if the result is greater than 9, we again add the result by 6. You can see. So if I add the 12 with the 6, I will have 0, 0, 0, 0, 1, 1, 1, 1, 0, 1, 1, 1, 0 is 0, 1. Now if 1 is written here, you can see that if I omit this one, 0, 0, 1, 0 is equal to the 2. And this one represents this one. Because we said that in the case of the BCD, we write the BCD, corresponding BCD of each number, something like that. So in this case, 8 plus 9, write 8, write 9. If you do this addition, you will see that you will have the carry. It means that the result will be 5 bits instead of 4 bits. Again, we know that the 5-bit is greater than 9 and also is not BCD because the BCD has to be represented by just 4 bits. In this case, again, we have to add the result by 6. If I add by 6, I can get this code. So in this code, from the right side, first 4-bit represents 7. And the last one represents this one. We know that the left side zeros is not important, but you have to we know that we have to write the zeros here because we want to represent it in the BCD form. But anyway, this code now is correct and is represented in the BCD form. Now, suppose that we have 3 digits numbers, 2 3-digits numbers, and want to actually add these numbers together. How we can do it? Listen carefully. I want to explain it in detail in the whiteboard. Okay, now suppose that we have 184 and 576. Now I want to add these two numbers together, but in the BCD form. So if I write the BCD code of the 184, I will have 0, 0, 0, 1 for the 1, 1, if I write it here, 1, 0, 0, 0, and for the 4 I have 0, 1, 0, 0. Now what is the corresponding BCD of the 576? In the case of the 5, I have 0, 1, 0, 1. For the 7, I have 0, 1, 1, 1. And for the 6, I have 0, 1, 1, 0. Now, we want to add these code with together. Listen carefully. Again, we say that we start from this side, like the normal addition that we do it. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 1 is 2, which make the 0 and 1. 1, 0, 0 is 1. Now, if you look at to this code, you can see that this is equal to 10. Here is 8, here is 2. 8 plus 2 is 10. So, you see that this value is greater than 9. In this case, we say that because this value is greater than 9, we have to add the result again by 6. 0 plus 0, 0. 1 plus 1, 0, 1. 1, 0, 1 is 0, 1. 1, 1, 1 is 1, 1, 0 is 2, means that 0. Now this 1, which now you can see that here we have the carry because this is the 2, 2 is 0, 1. This 1 is written here. This one is written here. Now again, we continue the addition. 1, 0, 1 is equal to 2, 0, 1. 1, 0, 1 is equal to 2, 0, 1. 1, 0, 1 is equal to 2, 0, 1. And 1, 0, 1 again is equal to 0, 1. Because it's equal to 2, 0, 1. Now, if you look at to this summation, again, you can see that this is great. This is the 5 bits. Again, means that greater than 0. Sorry, greater than 9. What should I do? Again, I have to add by 6. 0, 1, 1, 0. Again, if I do this addition, 0, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0. Now this one that comes from here again is written here. Now, if I start to addition this one again, 1, 1, 1 is 3, means that 1, 1. 1, 0, 0 is 1, 0, 1 is 1, 0, 0 is 1. Now, if you look at to this code, you can see that is equal to 7 and is less than 9. It means that directly you can write this one here. So, if you look at to this result, you can see that this is 7, this is 6, and this is 0. And if you do this addition, you will have something like that, which is equal to together. So this is the way of adding two numbers in the BCD code. It is so important. You have to notice this matter. When we have the result greater than 9, we have to add 6. Okay, let's continue. Now, we can say that we have another different types of the binary codes. One of them is the BCD that you can see here. The actually weighting of the BCD is this 1, 2, 4, 8. Now we have the another type of the code which is called as 1, 2, 4, 2. You can make the numbers from 0 up to 9 using these weights. For example, if you want to make 1, the corresponding binary code of 1 in the 1242 binary code, you can say that instead of 1, write 1, the rest is equal to 0. So this is the binary code of the 1. Similarly, for the case of the 2, we can say that instead of these 2, I write 1, the rest 0, so you will have something like that. So the question is that, do we have another binary code in this code 42? Yes. If we write 1 here, the rest 0, also we can produce 2. For all of the other codes, using this method, you can produce the corresponding number in the decimal. Another code is access tree. What is the access tree? If we add 3 to the 0 up to 9 and write the corresponding binary number, you can find the access tree. Look at here, this is 0, 0 plus 3 is 3, now this is 3 with the same BCD. If we add 1 to this BCD, will be equal to 4, and this is 4. 2 plus 3 is 5, you can see that this is 5. 3 plus 3 is 6, you can see that this is 6, up to the end. Another code is this code with these weights, -1, -2, 4, and 8. Again, like the 1, 2, 4, 2, we can produce the numbers using these weights. For example, if I want to produce the 1, if I make the -1, 1, -2, 1, and 4, 1, 0, and 8, 0, I can produce the 1. Why? Because -1 plus -2 is -3, plus 4 is the 1. So means that 0, 1, 1, 1 is equal to 1 in this binary code. All of the other codes can be written in this form that I have explained. We have another code, binary code, which is called as gray code. So this gray code is one of the most important codes that can be used in the digital system when we want to design it. Especially in the industry, this code is used. If you look at this code, you can see that this code has the advantage. One advantage of this code, which is written with the 4 bits, is that if you look at each 2 codes, you can see that there is just a 1 bit difference between these 2 codes. This bit and this bit are different with together. The rest is equal. If you look at these 2 codes, you can see that the difference is just in this 1 bit. In these 2 codes, if you look at, you can see that you have 1, 0, 1, 0. The rest is the same. Something like that for all of the codes. You can see that these actually gray codes just in 1 bit are different with together. So how we can produce these codes? We have one technique which is called as gray mirror technique. Using this technique, we can produce and generate the gray code. The first step is that we write 1 bit 0 and 1. Then we mirror the codes around the vertical axis. After that, we add 0 to the MSB of the original code and 1 to the MSB of the reflected code. Then again, we mirror all of the new codes and repeat these step 3 and step 4. How we can do it? Listen here, I want to explain it and I will show you that how we can do it. So, as the technique says, we write 0 and 1. Then we mirror it. Means that write 1, 0. When we mirror this code, we will have 1, 0. Then the technique says that write 0 to the MSB of the original code. This is the original code. And write 1 to the MSB of the reflected code. So now I could produce the gray code using 2 bits. If I want to continue it, again, I mirror the code, these 4 codes. If I mirror these 4 codes, I will have 0, 1, 1 1, 1 0, and 0 0. Again, according to this concept, this is the original code. Add 0 to the original code and 1 to the reflected code. Now, if you look at here, I could produce the gray code with the 3 bits. If I continue it, again, mirror this code, I can say that I have 0 0 1, 1 0 1, 1 1 1, 0 1 1, 0 1 0, 1 1 0, 1 0 0, and 0 0 0. Again, for the original code, add 0, something like that. For the reflected code, write the 1. Now you can see that I could produce the gray code using the mirror technique. Okay. We have another important binary code which is called as ASCII code. The ASCII code is the American Standard Code for International Interchange. We have 128 characters that using these characters we can write the message, we can write the text, and also we can write the anything. So the question is that when we write the message, when we write a text, how we can represent these alphabet or these symbols like dollar, right, greater than, right, less than, or the other, for example, question mark, or the other symbols, how we can represent these symbols and alphabet with the binary code using with the 0 and 1. Using this ASCII code we can do it, because 128 is equal to 2 to the power of 7. So for this reason we can say that using these 7 bits we can represent all of these symbols. Here you can see that all of the 128 symbols and alphabets, that using the 7 bits you can represent them. How we can represent a symbol using this table? Look at here. At each row of this table we have the 4 bits that represent B1, B2, B3, B4. And at each column of this bit, of this table, we have 3 bits represent B5, B6, B7. For example, if I want to represent the T, for the first 4 bit from right, we write the corresponding 0010 bit of this row. Look at here, because T included in this row, I write the 0010 as a first 4 bits, B1, B2, B3. And for the last 3 bit of T, we write the 3 corresponding bit of the column. Look at here, because T is in this column, instead of B5, B6, B7, we write 101. Similarly for the other symbols, for example, this is the ampersand. For this symbol, we have 0110, and for the last 3 bits, we have 010. Using this table in this form, we can find all of the actually ASCII code of each symbol. The last binary code that we will consider in this course course, is the error detecting code. What is the error detecting code? As you see, we can represent the ASCII code with the 7 bits. Now we said that normally we like to represent an information with 1 byte, which is equal to 8 bits. So the last bit or MSB bit of this actually code called as or indicate the parity. What is the parity? We say that a parity bit is an extra bit included with a message to make the total number of ones even or odd. Okay, so if we suppose that we have the even parity, means that in this actually ASCII code of the A, which is represented here, we add one another bit as a MSB and make all of the ones even. So if you count the number of the ones here, you can see that 1, 2. And because we want to use from the even parity, and the number of the one here is 2, we write the 8th bit or MSB of the our binary code as 0, because here the number of the ones is even. What about the capital T? The ASCII code of the capital T is this, and again we want to use from the even parity. So if we count the number of the ones, 1, 2, 3, so it means that the last bit has to be written as 1 to make all of the ones as even. Or if we use from the odd parity, we have to write the parity bit so that make the number of the ones as odd. Here the number of 1 is even. Now with adding the 1 here in this code, we make the number of the ones as odd parity. Similarly for this case, using this method, the sending and receiving systems can understand that, especially in the receiving system, can understand that we have error in the code or not, because always check the number of the ones in the case of the even or odd parity.